and it's wonderful that GROMACS has been able to support the GPUs for as long as it had. That introduces some new aspects to how to run GROMACS, and that's the topic of today's workshop for the next 2 hours. So if you look at the living document that you can see in the question next door, no, there's no slides yet. You see there is a link to the workshop page. I will share my screen and show you what I'm talking about. So in the living document, if you scroll down to, no, it's not the right screen. Let's do this one. Right, there we go. If you scroll down, there's a link here that will allow, if you follow that link, you'll be able to follow along the materials as I'm talking. And there will be links there that allow you to click through to further materials, background reading, and also get access to the couple of exercises that we will have that are good to do either as we're going along in the workshop or on your own time later, if that's convenient for you. If you have access to the Navigator cluster, then the workshop materials are available there already. You can see some instructions here about how you can get access to those. So that means you don't need to download the bash scripts and TPR files that we will use to submit some GROMACS jobs while we understand the kinds of characteristics you can see in running GROMACS on GPUs. If you don't have access to Navigator, that's fine. You can still do the short activities we have here if you have access to GPU cluster elsewhere. But unfortunately, you're on your own for getting your files there. So perhaps tools like wget or curl might help you get those materials transferred. And you can find the links that you would want to use with those from the web page that I've followed through. So I'll move on to the introduction of the workshop. If you have any questions, please do write those in the living document. I'll pause periodically and check for those. I am working from home, as is the norm still here in Sweden, and unfortunately my 1-year-old son is next door. So if he makes more noise than is a problem for you, then please do speak up and we'll try. Usually he's quite quiet and things work well. So the first question that this opening lesson will address is why do we care about getting good performance from our GROMACS simulation? When should I care and when should I not? And we want to understand that because one of the other objectives of this lesson is that we want to know the scientific value of GROMACS performance. There are many times we don't need the best possible performance. Sometimes we just need good enough. Sometimes we just want the easiest thing that we can do. And so this lesson will give us some insight into these kinds of questions. As you probably gained the knowledge yesterday, molecular dynamics iteratively solve equations of motion that sample a thermodynamic ensemble. There's many iterations that are looking at a set of positions, that are computing the forces, using those forces to update velocities, and then using those velocities to update the positions. Those time steps that get repeated many, many times are around about the size of a femtosecond, whereas as we know, not much in biology happens in less than milliseconds, and indeed there are many processes that take years or decades. So it's clear that these iterations that we're going to do in our simulations need to be extremely fast in order that we can do enough of them that steps of 10 to the minus 15th of a second get done often enough that we get up to timescales of 10 to the minus 6, for example. So we need to be doing billions of these steps. So there's a lot of engineering effort going into GROMACS to make sure that we use the computer power to the max so that that can be done in as little human time as possible, because all of you are doing courses or submitting grants or conducting research, and you prefer to have your answers sooner so that you can give guidance to your experimental colleagues or publish a paper or do further computational experiments depending on how the workflows look. So these time steps that we've been talking about are normally femtoseconds, and it's important that we make sure we do things as efficient as possible. That's well known to the GROMACS developers, of course, and they put a lot of effort in to make sure that GROMACS will use all of the hardware that is available on your computer as efficiently as possible. However, that's a little difficult to do because you've also given GROMACS your own simulation. There's a lot of characteristics of your simulation system that GROMACS wasn't engineered specifically for. We know what people typically use, but your use case might not be very typical. So understanding some of your options is valuable because sometimes the automated defaults don't work as well as one might prefer. That's life. We'd love to be able to do better, but it takes time and a lot of effort. We're slowly working on it. So when you just run the MD-run command line tool, it looks at the hardware and does its best. So today we're going to learn about some of the ways you can observe what it did by default, and then perhaps try some alternatives. However, we also need to be aware of when do we not care about the performance. There's plenty of times when you could spend your effort to say, oh, I can get this computer program running faster. But if you're spending too much of your time and not enough value from getting the computer to run faster, that's overall not a good trade. So if you're doing something that's a very short-lived task, like just minimizing or incorporating your MD simulation, generally you should just accept the default performance. GROMACS's defaults will do fine. But something you're only going to do once, like sitting in a tutorial or reproducing somebody else's work, don't worry much about optimizing. The defaults will be good enough for you. Likewise, if you're just beginning your work with GROMACS, you're probably overwhelmed by thinking about all the different options and the different kinds of methods you can use and reading lots of papers about how people have used them in the past. Focus on learning the new things. Don't worry about performance. These are things you want to worry about if you are running the same simulation for weeks to months. Then you want to understand how it should run most efficiently. If you're not going to be running a simulation for more than a week or so, go read another paper. Go design another experiment. That'll be much better scientific use of your time than worrying about how to get GROMACS performance working best. When it does matter, there are a bunch of ways to make sure that you're doing the right kinds of things before you even start running the simulation. Typically, you'll be running these simulations on a cluster somewhere where the system administrators will have installed GROMACS for you. If they haven't installed it for you, then please do ask them to, because they know a lot about how their cluster works and they can do a good job of setting GROMACS up for you. And there are plenty of ways that they can get further guidance from the community of system administrators out there. So very often there'll be a version of GROMACS on your system, and you should definitely take advantage of that. However, a little bit of awareness on your part can provide some guidance to them in cases where they're not GROMACS experts, whereas you're becoming a GROMACS expert. You might be able to see some things based on what you see in this tutorial that will help you understand whether things might be able to be improved. So every time one runs GROMACS, it prints an output to the log file that reports the same kind of information we can see here. You can also get access to this information if you just run the command GMX -version. It'll print out a table a little bit like this. And you can check interesting things. So one should typically always start a new scientific project with the very latest version of GROMACS. We release a new version every year, and we update it a few times during the year. So the major version number is the year of the release. So the current one is 2021. And the current patch release is 0.3. So every couple of months we update that. So the first one doesn't have a patch number, and it's 0.1, 0.2, 0.3, and so on. So you very much want to use either this year, maybe last year, and the highest patch number that's available. So you might find that on your cluster, the system administrator did an install last year for another user who asked for it, and hasn't updated it since. Please do ask them to start your work with the latest version so that you take advantage of all of the improvements we do and have done since the last year of GROMACS. There's a tremendous amount of work that goes in, and the code is getting better all the time. There's a few other details about how GROMACS was configured and how it was working on the hardware that are important to think about when you look at this output. The key one to start with is what precision it was built for. Many scientific applications are built to use what is called double precision, where the arithmetic is done using very many more bits to describe floating point numbers than are necessary for GROMACS. So GROMACS is able to run in that mode, and there's a few occasions where you might want to do make sure that the build you're using is a single precision build. So make sure it says single here, not double. Looking at the GPU support line, you want to see that it says CUDA here if you're running on the typical clusters that exist in production right now. Shortly that'll change. There'll be a range of GPU supports that are good to use, but you want to make sure it doesn't say none here, so you know that you have the ability to get GPU support when it's available. If you are running on the CPU, then you want to make sure that the FFT library is reasonably up to date. 3.3.8 or 9 is fine. And there should be a suffix here. Don't worry about what that means, but this suffix indicates that it has been compiled for the capabilities of the particular pieces of hardware that you're going to be running on. The system administrator will take care of those details, but if there isn't anything here, then there's something that can probably be done better. The next most important thing is that the compiler is modern. GROMACS itself requires a fairly modern version of C++ to be compiled. So these days, most of these versions are okay, but you can still get some nice wins from making sure it's the latest version available. So currently, the latest version of GCC is version 11. So if I was looking at this log file, not only would I say to my admins, hey, this is a year old, but also it's using a relatively old version of the compiler. Can we update those? There's a little bit of a caveat there that the CUDA versions lag a little bit behind, so you might not be able to get the latest compiler. But the latest one CUDA supports is good. By default, this would always show -03 and -d and debug. You definitely want both of those. There'd be no reason this would change unless your system administrator did something quite strange, but it's worth checking for those two. Last of all, we should also look at the versions of the CUDA driver, which is a little program that sits alongside the operating system and makes sure that user programs such as GROMACS can talk to the hardware, and the runtime, which is the library against which GROMACS has been linked. It's best if both of those are the same version. It's okay if the driver is newer than the runtime, and if the first version is at least 11, it's okay if it's older. That's a very new development from NVIDIA that is good, but you can be sure you won't have any problems if they're identical. So that's something to check for as well. So that brings us to the end of the introductory lesson. We've talked about some of the reasons why you might care about getting high GROMACS performance. We also talked about occasions when you don't want to worry about it. You've got something better you can do with your time. And we've talked a little bit about some easy wins you can have checking via GMX version whether the GROMACS that you might be about to use is a suitable one. And if not, you might either want to install GROMACS yourself, for which we have an extensive install guide available, or ask your system administrators to do that work for you. I'll pause at the end of this lesson and ask if there are any questions on the material so far. I see there aren't any in the living document. Is there anything people would like to ask at this point? We can take questions verbally as well. If not, then we'll move on to the next section. Those of you who are following along at home, you can click on these next links and you'll get taken through. So I'm going to give a little bit of an overview of the hardware structure of Navigator, which is the GPU cluster available to researchers in Portugal. This is going to be directly useful to you if you might be running simulations on Navigator. But if you're going to be running simulations on some other cluster, it's still good insight for you to have available so that you understand the sorts of things you may need to think about if you're reading, for example, in the GROMACS user guide, how to run these simulations well. So the kind of questions we'll be able to answer at the end of this lesson is what kind of hardware is available on Navigator's GPU nodes, and how should we organize the computational work to go where it should. Indeed, what does go where it should even mean? We'll understand that the time that it takes to transfer data to do computation on is finite, and we need to manage the locality of the data and the tasks that use them, which is quite important for performance. So in high-performance computing, HPC, there's a very clear trend towards providing most of the computational power from computational units called GPUs, or graphics processing units. These are typically much beefier forms of the same kind of hardware that you have in your everyday laptops. These too can be suitable for running GROMACS on, but the ones you find in your HPC clusters are much better engineered. It's like the difference between a Formula One car and an everyday passenger car. They've just got different kinds of engineering in them that are built for performance. So many applications, including GROMACS, have been ported to run on these GPUs. Almost all GPUs that are in service today are made by NVIDIA, and their CUDA programming framework is pretty much universal in HPC applications. That is changing. AMD and Intel are bringing in new kinds of hardware that have won major contracts for supercomputers around the world, and so we will see that landscape changing as time goes on. The GROMACS developers are hard at work making sure that GROMACS will also work on these GPUs, and all the lessons that we learned today will be able to transfer directly. We don't want any of this leaking into your heads, and so we're working very hard to make sure that's true. All such machines will have the same general characteristics. There will be very many CPU cores, perhaps separated into a few physical units called sockets, and there will be a handful of GPUs, each with very many numbers of cores, typically thousands, that are all less powerful than CPU cores, but are able to be organized together to work in concert in a way that the CPU cores don't do as effectively. It's a little bit like watching an army on parade versus watching school children running around a playground. The GPUs are very much like an army on parade. There's thousands of the same thing doing exactly the same thing at the same time. If you are able to get your job done in that sort of lockstep pattern, then using GPUs is superb. However, if you need to do a lot of different things, then you want to be more on the school children running around the yard kind of model where everybody can do something independent and very few interactions happen also. So the GPUs are much more like the army on parade. So on Navigator, we'll look at the hardware layout. So I used a program called LS-Topo to produce the data that I've made into an image here that describes how the nodes that have GPUs have 2 GPUs on each node. Like all modern hardware, I don't know of any exceptions to this, it's built around the notion of non-uniform memory access. Some parts of the memory are closer to a particular computational unit than any other. So to get best performance, the programmers of the code and the users of that code might need to be aware of how close some processing units are to each other. It doesn't matter, as I said, whether you're using Navigator or not. The same sorts of lessons will transfer to other GPU clusters. I needed to use a specific example so that I can talk about things, and so I used one that some of you may have access to. So in this particular case, Navigator has small sort of fits. So there are 2 different sockets on Navigator. So we can see these in the olive green on the outside, which contain some structure within them. We don't need to worry about that at the moment. That separates groups of 10 cores from each other. So we can see here that there are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 CPU cores, each of which has 2 processing units. Sometimes these are called hyperthreads. So it's quite common that on your laptops or desktops, hyperthreads are very effective for letting one program that is running do some work while another program is waiting for user input or waiting for a file to come on disk. That tends not to be so useful in HPC. It is slightly useful for GROMACS, but you will see a little bit of variation here. Sometimes there will be multiple hyperthreads enabled on the cluster, sometimes not. You see that these groups of 10 cores are repeated 4 times. There's 2 groups in the first package and 2 further groups in the second package. We can also see here that there are some GPUs reported by this hardware detection package. There's card 1 is here attached in group 0 of package 0, and there's card 2 attached in group 0 of package 0. There are no GPUs, however, attached in the second package. Instead, we see here attached the network link. So it's important in HPC. You're very often using more than one node, which you can think of as a roughly analogous to the compute unit that is in your desktop or your laptop. In an HPC center, typically many hundreds to thousands of those are networked together and are able to be working concertedly on the same problem. So the network is connected to a different package than the GPUs are connected. So we have here, firstly, the observation that if we are trying to do some computational work on the GPUs, if our data is close to core 36, for example, it's relatively far from GPU card 2. If the data was on core 15, it'd be much closer to GPU card 2. If, however, it was on GPU on core 15, it'd be close to card 2, but not as close to card 1. So we would expect that trying to organize work that is transferring data between the CPU and the GPU belong best here in group 0. Work that involves transferring data between card 1 and any of these cores is best placed in here. And we'd prefer to do work that involves the network out on these cores. So that all seems straightforward. The problem for the developers of these sorts of packages is that this is not the only way the hardware might exist. We might have GPU card 1 here, GPU card 2 over there, and the network back in group 0. Now, there are ways for the developers to find out how these things are organized. That's not always available to us at runtime. So being aware of some of these aspects of structure can be helpful in some situations. So we'll move on to the first quiz. Unfortunately, I'm not a host here, so I can't do an interactive Zoom quiz for you, but we can think about it here. And when you've thought about it, you can click here on the plus symbol to see the solution. So which range of CPU cores do we think would be least effective to use in work related to card 2? So here in the diagram, we see card 2. Which range of CPU cores would be least effective to use in the work there? When you've thought about it and chosen your answer, have a look at the solution. Give everyone another few seconds. Okay, I'll spoil the answer. Correct answer is either 3 or 4. The cores in the second 2 numenode regions, second 2 groups, are further away, so they're least effective to use with card 2. Data transfer will be less efficient. Great, so let's move on to some technical details of running jobs on Navigator. If you're using some other cluster, these will often have some minor differences, but also a lot of similarities. The particular job scheduler they use on Navigator is called Slurm. That's a very popular one, but there are others out there. You might see Load Level or OpenPBS. They all do the same general job, which is allow you to ask the cluster, please do this computational work for me. I've described what I want to do in this bash script. I've described what kind of computational resources I need and for how long with these lines, and then what I want you to do in these following lines. So then the scheduling program takes all of the information that you've given to it and looks at all of the requests that all of the users make and how many resources are available, and it plays a game of temporal Tetris, if you will, and decides who can use how much computer when. So it uses information like how much time you've requested to work out that, I have one user who wants multiple GPUs for a long time and several users who want one GPU for a short time. I'll schedule all the users who want the GPU for a short time first, so that when they're all done, the person who wants it for a long time can then have it for a long time, and everybody gets their results back better than if I run the long job first. So it has a complex algorithm that does that game of Tetris for you. That might mean sometimes that you submit to the queue and then have to wait for it afterwards, but that's life in a shared resource. If you've got a lot of money and can buy your own supercomputer, then good luck to you, but otherwise you're very likely to need to share using this kind of structure. So The Sloan job shader is capable of quite complex assignments. You can ask for lots of GPUs and lots of nodes, but today we'll focus on one that's just going to have one or more GPUs and matching groups of 20 CPU cores. If you follow this link, then you'll see that there's a useful guide produced by LCA that allows you, gives you a bunch of background information on what these SBatch commands mean and how you manage running them and checking they're running and what happens if they died. So any cluster you use will have similar web pages, so you should very much make sure you know where they are and how they are structured, so that when you want information from them, you know where to go. So if you're running this workshop on your own, you might want to read that documentation now to have a look at how do I get a single GPU with some CPU cores, because you might want to vary some of these parameters. If you're using Sloan, and you will need to change them if you're not using Sloan. So without further ado, let's switch to Navigator. I will copy.
So Mark, you've got some questions in the live doc that could be good to answer.
So I'm going to leave all of those for later because they're not about the topic we're talking on now. I'm very happy to talk about those sort of questions, but I don't want to distract the students who don't have those questions from the topic at hand. But yeah, the good questions, I'll get to them. Okay, so I'm going to switch to running on Navigator. So I'm going to change to my workshop directory in my home directory. And there we have nothing at the moment. So I'm going to use VI to open an editor window. I'm going to say, let's call the file run GROMACS shell. That's going to open an editor. Tell VI that I want to edit a file, and then I will paste in content I just copied from the web page. Okay, I don't actually need srun, but so here what I'm going to do is load the standard module for GROMACS, and then I'm going to run GMX MD run on it. I don't actually want MD run at this point. I will just to see. So I'm going to change that. You can leave the script as it was and try it on your own. I'm going to now use the command sbatch sh.
Sorry, Mark.
Submit that to the job. Yes.
I've created reservation for you, so just to make sure you had a GPU available.
Okay.
So you're going to need -- reservation equals GROMACS workshop.
Right. Like that?
Equals. If reservation equals.
Reservation equals GROMACS -.
And one word, no minus.
Great. Thanks, Miguel. Okay, so that's a modification that any of us who are following along on Navigator will want to make in scripts. If I get a break later, I might be able to do that in bulk for you. But for now, let's run that script. So Sloan tells me in reply that it's submitted batch job 85386. So we can see if we go back to the no, I didn't have any further comments there. So we can check, for example, all of the jobs that are running on the machine. We get a big long list of all the things that might be happening. My username, however, is Mabraham. So I was able to find that by asking the system, who am I? So let's have a look whether any of the output by Q is relevant to a job by Mabraham. No, that means it's already finished. Okay, cool. So I can see, okay, there's the output from Sloan. It added this long number that is the output. have a look at what's going on in that file. And so we see here that indeed GROMACS 2021.3 is running. And we see here the same kind of output that we were looking at previously. So we can see that it's version 2021.3, so that's great, it's the very latest version. However, we see here that it's GPU support disabled. So unfortunately, Miguel wasn't able to get a version of this installed in time for us. It's my fault, I asked him a bit late. It's got a quite recent version of GCC, 10.2 is quite recent, and everything else is more or less in order. So this is just illustrating to you that it's worth doing this kind of check to find out whether you're even able to run on the GPU. When the GPU support is disabled, well, we won't be able to use that. So
actually, after we've talked, there is an enabled version now.
Okay.
Sorry for the interruption.
That's all right. How would you suggest I use it?
If you do ML avail GROMACS, it's the one with FOSS-CUDA on the, so it should be that. Yeah.
So this is stuff that you will need to get familiar with when you are running on a cluster. There's a library of different pieces of software that have been installed, and they're organized into what are called modules. And so there are many versions of GROMACS that have been installed, and this one here, FOSS-CUDA 2020B, will have GPU support, so we'll use it in today's workshop. I had my own prepared if there's a problem there, but for the exercise, I'm now going to change that. So we've said to the module system, please load GROMACS 21.3 with CUDA support. And now I'm going to submit that command again. And it'll probably run quite quickly. So now we see there are two different out files. They've got different numbers. Those numbers get higher over time. So I will look at the larger one. Now, see, wonderful. It has got some CUDA support. Great. It has also got a few other things that are interesting. Okay, so GROMACS recently changed to be mixed precision rather than single. That's fine. Mixed means the same thing that single already does. It's just a little more accurate. That's good. There is SIMD support. The compute nodes here do support higher levels of SIMD. So if I was going to run production simulations here, I might ask the system admins to get AVX512 support organized. GCC version is quite reasonable. Things have been optimized suitably. And CUDA driver and runtime are both very recent. So this is perfectly good for purposes of running GROMACS. If I was going to run months worth of simulations, I would definitely get that fixed. For today, that's good, great. So let's call this exercise pretty much done. Are there any questions related to getting this sort of troubleshooting working on Navigator or general questions? I'm sorry, I can't help individuals running on their own clusters because I don't have time. But it's worth taking for everybody else in the workshop. If you aren't able to get it running on your own cluster relatively easily, then please do just follow along as I'm working. You will still learn some things that way, and then perhaps afterwards you can have a go at the material in your own time. Are there any questions about this sort of investigation? If not, then we will go back to the lesson material on the website. So you might want to, when you're doing this sort of thing yourself, check out the cluster documentation. That's always your best friend. The helpful system administrators are also only an email away, so make sure you learn how to do that. Do, however, look at the documentation before you ask them, because you will learn better that way, and your karma will be good by the time you need to ask them a serious question. So the key points we've learned today is that HPC nodes have internal structure that affects performance, and that over your life in using HPC resources, you should expect to see clusters that look like Navigator, that have multiple GPUs per node. As time passes, there will be ever more cores and GPUs on these nodes, So expect to see complexity. Fortunately, most of the time, the developers of these packages will have dealt with it for you. GROMACS does a relatively good job at that. If, however, you're using other HPC packages on these machines, be aware that sometimes you are very much left to fend for yourself. And so this kind of background information is valuable for you in your wider journeys through computational science. Wonderful. How's time going? It's 10:40. All right, let's get started on the next lesson. We'll take a break after about 15 minutes so that everyone can stretch their legs and so on. So we'll move on to the next exercise. We'll talk about how the MD1 algorithm works and what are the most important aspects of it, considering how to get it to run fast. And what do I need to know as a user to understand what the performance reports from GROMACS is going to be telling me. We're going to have as objectives from this lesson that we're able to name the most important parts of the MD workflow, and we can appreciate some of the internal architecture of MD1 so that we can understand what the log files are telling us about performance. So the workflow within any MD simulation, not just GROMACS, this is the same in NAMD or OpenMM or any of the other AMBER, any of the other big packages out there, all do roughly the same thing. There's a startup phase where it reads your user input, then it gets set up, builds some data structures, does a bunch of structuring and housekeeping. Then it moves into a stage where it computes the forces from the current positions of all the particles. So that's the most computationally demanding. It tends to take the most amount of time. And that's because there's a lot of arithmetic. You have to find out how far all the particles are from each other. And you have to put those through some relatively simple mathematical functions to compute the forces from the derivatives of the potential energy. And then you have to add up all of those forces so that you find the total force on each atom. Once you've got the total force on each atom, you then run that through code that might be called the update, where the forces are used to change the position slightly. So basically you multiply the force by the size of the time step and use those to update the positions, the velocities. Then use the new velocities to update the positions. Perhaps if you're using a constraint algorithm like links or shake, which is very commonly used in these simulations because it lets you have a larger time step, then the constraints module will run. If we've got to the end of the simulation, then we would now stop at this point, but typically you're doing this for thousands or millions of steps, so we would now go back to the start and compute forces based on the new positions. So this iterative pipeline runs thousands to millions of times during MD. And how fast it takes to run depends how fast the arithmetic is and how long it takes to move the data to where it needs to be for the arithmetic to be done. One of the facts of life when using a GPU is that it's physically far away from the CPU as far as a computer is concerned. It's still only centimeters to millimeters in your actual hardware, but it takes time for the electrons to be transferred there, and all of the infrastructure that transfer them takes time to do that work. So moving the data around takes you time. That physical separation is quite difficult to get around. And in general, which one dominates is hard to understand. The good news is that most of the arithmetic is in this force calculation, so there's a natural place for the developers to focus their effort. And it turns out that's the same sort of consideration would be for you as users understanding how to manage this best. So as I was saying earlier, GPUs are electronic devices that are massively parallel. There's very many of the same work are working together. And it works best if they're all doing the same thing at the same time. This was developed for the challenge of rendering complex images on computer screens, particularly for complex things like 3D computer graphics. But the good work that was done there is also built upon so that we can do more general computation. These days in HPC, it's very rare that an application has no support for GPUs. And that'll become more rare still as the developers catch up with the times. However, before parallelism ever helps us, we need to know that there is concurrency, i.e. that there's independent pieces of work that can be separated out. Your experience of working in human teams has already taught you about these ideas of concurrency and parallelism, even if perhaps you haven't used those words to talk about. If you're working on a team project, if there are two of you working on the same aspect, you're going to have to talk with each other closely to make sure that you don't repeat the same work or do things that are inconsistent with what each other are doing. If, however, you're working on, say, separate parts of the same document, or there's 10 of the same thing that has to be done, and you can just do your own one in isolation, then you have what is called concurrent work. We also see similar sorts of challenges in time. If it doesn't make sense to work on part 2 until part 1 is done, those pieces of work are not concurrent. If they're not concurrent, then we won't be able to do them in parallel. If they are concurrent, then we may be able to. That depends how the code has been written. So in the example I've got here, if Mary can't start her work till Nash is done, hopefully Mary has something else to do. However, if Mary doesn't have something else to do, then Mary's either going to sit twiddling her thumbs, or Mary will have to go and do something else. And then when Nash is done, she can now perhaps start her work. That tends to be inefficient for both humans and computers because of the cost of switching context. So if you want something to work really, really well, you want to have all the hardware working on the same thing all at the same time. And if it's not able to do something, you want it to just wait until it can, rather than going off and doing other work. So GROMACS is particularly sensitive to this. Other kinds of computer programs like Microsoft Word and the browser and so on, they're built to be concurrent within each other, because it doesn't matter too much. Most of the time your word processor is sitting waiting for you to type a letter in a new word. Most of the time your browser is waiting for you to move your mouse and click on something. It doesn't matter if somebody else borrows the CPU resources in the same time. That's not true with GROMACS. We're using all the CPU resources within the next microsecond. So please don't interrupt us, so to speak. Fortunately, the forces that we need to compute naturally come in a few classes, and those happen to be concurrent. In a typical simulation, we have bonds between atoms in our chemical system, and we have the need to evaluate short-range non-bonded interactions. So those are based on how far apart the atoms are from each other. And those are separated into two categories, short and long-ranged. Those two parts of work are also concurrent with each other. And there may be some other stuff as well, such as the forces introduced by AWH that you might have heard about yesterday. So there's a wide range of things that have to be done that don't depend on each other. We can compute the bonded forces without needing to know anything about how the non-bonded forces are being computed. So this naturally gives us sources of parallelism because we have concurrency. These different kinds of chemical interactions are very valuable to us as developers of GROMACS, exposing to you, the users, the ability to get this kind of parallelism. The crudest kind of parallelism we can exploit here in these kinds of computers is to put some of the work on the CPU and some of the work on the GPU. If we're able to balance that well enough, then you will get all of your compute units working together, and the overall amount of time it takes to work reduced. Within each of these kinds of components, there's further parallelism. We won't be talking about that today, but it's just worth being aware of that topic. So let's move on to our next quiz. Please do have a think about this and answer it to yourself, and then click on the plus symbol down here to see the answer. The quiz is, what is the best reason for moving the most computationally expensive tasks to the GPU? Is it because they cost more? Is it because the CPUs cost more than the GPUs? Or the GPUs are good for computationally expensive tasks? It's simplest, or it makes room for many different kinds of tasks on the CPU? Have a think about that and then choose your answer. I'll give you a few seconds. So given that GROMACS already had a fast CPU implementation, moving the biggest workload to the GPU provides the best parallelism. There's little bits of truth in the other answers, so don't feel bad if you didn't choose number 4. It's a little bit deceptive, this question. What we want to move, given that we can run all of these tasks on the CPU already, one we want to move to the GPU is the most computationally demanding, because there are more resources available on the GPU, so that we can get more impact for the parallelism by moving concurrent tasks. There are some kinds of simulation you can do with GROMACS and similar packages where it's enough to model the non-bonded forces by treating only short-range interaction. Because things like the Coulomb electrostatic interactions decay as 1 on the distance between them, after a certain distance, the interactions become negligible. You can also take advantage of the fact that in highly homogeneous systems, you get cancellation from similar contributions on the other side of the particle. If what I've got is a big box of water. If I have one particle here, another particle over here, which doesn't work very well in the background, another particle over here might have a contribution that is balanced by another particle over here. So you get further cancellation, even if the sizes of the interaction are not yet negligible. So the simplest way to do this is to say, okay, let's have a loop over each particle. And for each particle, we'll look at every other particle and we'll compute the interaction if the distance is within some predetermined range that we've measured and decided, okay, that's a large enough range that we can treat the interactions as negligible. That works, but it's highly inefficient because the particles move slowly enough that it's almost the same interacting set each time. When you've got such tiny time steps, you would need massive forces for them to move much. And it so happens that in an equilibrator system, you don't have such massive forces. The cost of that algorithm also scales with the square of the number of particles because you have to loop over every particle and then every particle for every particle. So it means you need n squared comparisons. And that's really ugly when n starts becoming large. So instead, all major MD packages build a thing called a pair list, which is a list of particles that are close enough to interact. That list gets reused many times until the diffusion of particles makes it necessary to rebuild it. Quite nice because once you've got the list, now you just go through the list for each particle. And so when you're doing the search, it's still roughly n squared. But when you're actually computing with it, it's only size n because you have a fixed length of the list, so it doesn't scale with n anymore. So how does this look once we get into our molecular dynamics simulation? This means we have to have a pair search at one stage. So we build this list of the particles that are near enough to each other that they're probably interacting. Then we use that pair list as input to our short-range forces. Go and run our update. Has the pair list been used for long enough? Yes, no. If not, go and reuse it again. So we often do 10, 20, 50, 100 steps in this inner loop where we're reusing the same pair list. And then when we're done, we loop back further in time and go and do a new pair list. So that if once diffusion has moved the particles far enough away from each other, then we'll need to rebuild the list, and that happens there. So particles are diffusing around. GROMACS automatically adds a buffer to the required distance when building the list. At each step, we check the distance properly, but we built the list so that it's got extra particles in it, some of which won't be interacting, but we don't know until we check at each step which ones will be. So that is a source of inefficiency, but to get rid of that, we have to compute the pair list more often. So we've got two different kinds of inefficiency to trade off. We don't want to keep recomputing the pair list, but we don't want to have lots of extra particles to compute on that aren't going to contribute to our forces. GROMACS will handle all these details internally for you. You can influence them, but you don't need to these days. If you look at old tutorial material, you'll hear discussions about how you might want to do things here, but there's no need to handle these details anymore. The current values are very defensive. We don't recommend you change them because you're only going to get a very small amount of performance benefit. So there's no need to get involved in this sort of setup anymore. BioXL did some fantastic work here a couple of years ago, making sure all this was automated. Berkes, who you were talking to yesterday, helped out with a lot of the theoretical work there, and many of us contributed to the implementation. I hope other MD packages are slowly catching up to this technology, but if you're using other MD packages, you may need to manage this yourself. It also turns out that if you're constructing these pair lists, if you're doing them on a single particle, it actually runs slower than if you construct these pair lists in terms of clusters of particles. This makes sense because if you would have, say, 4 particles close to each other, it makes sense that they will have most of their interactions in common with each other. So instead of a pair list between individual particles, it makes sense to have this pair list constructed from clusters of particles. That's more efficient overall because each of these clusters are normally either all interacting or none interacting with each other. So it's much more efficient to structure the calculation like this. These clusters have nothing to do with molecules or bonds, merely that they're close together, because here we're talking about the non-bonded interactions. In fact, on GPUs, it turns out to be even more efficient if we group the clusters into clusters of clusters, so that we have larger amounts of work to exploit the very low-level parallelisms available. Thinking now in terms of our soldiers marching on the playing field rather than our discrete compute units, which is the whole GPU. So in order that we can use those cores like the soldiers marching on parade ground more efficiently. We actually construct clusters of these clusters. But there too, we don't need to worry about those details as users now, just need to be aware that this is what is going on. Here we see an illustration of differences between a CPU-centric setup and a GPU one, where we construct these clusters of clusters.